welcome to our third part in the series on dark matter. Today we're going to be hearing from Blanco, who's at Princeton, on shedding light on dark matter, the campaign to directly detect dark matter. Take it away, Carlos.
Thanks, Ellen. Okay, hi everyone. Thanks for inviting me to give this talk. I'm really happy to be following up Tracy, who I think did a fantastic job of talking about indirect detection. And so I wanted to share with you all a broad overview of direct probes of dark matter and in particular, particle dark matter. And so I'm sure a lot of you have already seen introductory slides that talk about several of these things. But really, I just want to convince you that there are overwhelming bits of evidence for particle dark matter across many scales, from scales as small as galaxies to the largest possible scale that makes sense, which is the cosmological scale. And so I'll just briefly go over them and try to convince you that there is an unequivocal need for dark matter. And really, I will just tell you that can only be or that this evidence can only be reconciled with something that appears to be particle-like. Okay, sorry. So at the largest scales, the cosmological scales, we get information from the cosmic microwave background. And in specific, if we look at the small temperature differences in our map of the night sky in the CMB, we get this power spectrum, which tells us roughly how many patches of how big an angle in the sky there are. And if you look at the power spectrum, these peaks and troughs and their relative heights tell you something really important. It tells you that the universe is missing a cold, non-interacting fluid that can't be accounted for by regular matter. So that's a piece of information that just comes from looking at the light that decoupled at the Big Bang. If we then sort of fast forward and look at scales that are much smaller than that, but still quite large, things like galaxy clusters, we find things like the bullet cluster here, this picture in the center, which is a sort of canonical picture in dark matter. And what's going on here is we can look at images and measurements of situations where two galaxy clusters have interacted. They've crossed one another's path, and we can ask about where the mass is concentrated in these objects. So if we take a look at, for example, X-ray pictures of this merger, which tells us where the hot gas is, right? The concentration of where most of the visible matter should be. We can color that, and we can see that that sort of clumps together in the center. At the same time, we can say, okay, where is most of the actual matter? We can map that using gravitational lensing, and we can color that in blue, and we see that that's passed through without really slowing down. And so by all accounts, this is cosmological chromatography. This is a separation of two fluids. And that tells you that, yes, there are two different components. They interact very differently. And it turns out their relative abundances are just right to be called the dark matter in blue. And as you zoom in on galaxy scales, you find other very irrefutable evidence of dark matter when you measure the circular velocity of stars as a function of distance. And in fact, what you measure is that there is an invisible component of mass that is absolutely required to account for the plateauing of these circular velocities as a function of distance from the center of galaxies. In other words, you just need more mass than can be accounted for by what we can see to be able to pull on stars hard enough to keep them on track as they turn fast around the center of galaxies. And all of these pictures across scales really come together to tell us that our universe is roughly made up of 5 to 1 dark matter to ordinary matter. And so this is a very artistic rendition of what our dark matter halo looks like here with our Milky Way somewhere in the center, and in blue you have this roughly spherically symmetric dark matter halo. And somewhere on the arms of the galaxy you have Boston probably. And if we study the dynamics of stars in our Milky Way, we can sort of back out two important pieces of information. One, we can estimate that the local density of the dark matter is about half a proton per cubic centimeter. Okay, that's how much energy density there is of dark matter in our general neighborhood. And also we can do simulations and analyze what kind of velocity distributions would give us this abundance and would give us the galactic dynamics that we observe. And it turns out that the dark matter should have a mean velocity of hundreds of kilometers per second. Okay, that is rather fast, but non-relativistic, and that's important. What these two pieces of information also tell us is that for a given dark matter candidate with some mass, MDM, as the mass of the dark matter that you're considering gets heavier, then the relative number density gets lower. And that means that the average flux through any detector that you set up in your lab also decreases with increasing mass. That'll be important later on. Okay, so what about the things we don't know? Pretty much everything else. We don't know the bare minimum. We don't know dark matter's mass. We don't know that it's coupling, and we certainly don't know its production. And so what I want to tell you about is a general trend that I've noticed in the community, which is a general trend towards embracing this interdisciplinary approach towards creating probes for physics beyond the standard model in general, but in specific for dark matter detection. And I think there's a big return on investment from looking at things this way, where we're now finding out that techniques that have been developed by other fields are actually very useful in our hunt for dark matter. Okay, so how do you go about probing dark matter? Well, if I write just the simplest diagram of how dark matter here, dm, interacts with the standard model here, sm, I can write this quasi-Feynman diagram and allow time to flow in 3 different directions. If I have time flowing from the bottom to the top, what you see here are 2 standard model particles coming together, interacting, and generating a dark matter pair. Okay, these are the kinds of things that happen at collider searches. And so in places like CERN, what you might do is you might look for energy that's missing that the detector can't account for because the dark matter just streams out of it. Okay, these are collider searches. This is a fairly good way of looking for dark matter of a particular scale. On the other hand, if you take time going in the opposite direction, where 2 dark matter particles come together, interact, and give you a pair of standard model particles, in those cases, you might look for astrophysical excesses in observations of gamma rays or X-rays or what have you. And I think Tracy did a very good job of talking a little bit about that last week. And finally, if time runs from left to right here, you have a situation where the dark matter is just interacting directly with a standard model particle. Okay, and here the kind of signals that you're looking for are recoils. You're looking for a situation where the dark matter is donating some momentum, is knocking into or being absorbed onto a standard model preparation in your laboratory. And one of the things that I want to get across here is that the direct and indirect detection channels are able to cover many orders of magnitude in mass and in coupling strength, which is a little dissimilar from collider searches, whose scale is really set by the energy of your machine. Many asterisks to that, but broadly speaking, the direct and indirect detection channels are much more forgiving about what scale your physics in, and they can be applied very broadly. So let me now just focus on the direct detection channel and give you just something to keep in your head, a rule of thumb about budgeting, okay? If I'm going to allow the dark matter to interact, and I'm going to label from now on dark matter as this chi, and it's going to come in and it's going to interact here with some state in my laboratory, which I've labeled capital psi. And it's going to exchange some momentum q. It's going to then take that state that I prepared in my lab, and it's going to promote it to some final state psi f. And as it does, it's going to impart some momentum and some energy. And so we can ask, what's the total energy budget, momentum budget of this interaction? Well, the energy budget should just be the kinetic energy of the dark matter, which for a dark matter that is as heavy as a proton corresponds to keV energy. So these are like X-ray energies. And similarly, the momentum budget for a particle that's as heavy as a proton is of order an MeV. Okay, so these are just kind of orders of magnitude to keep in mind when we talk about what sort of size we should prepare to look for this kind of dark matter. And I also wanted to show you this cartoon of what the plots that we're going to be looking at today look like. Okay, so generally we talk about dark matter living in some parameter space, and a very general parameter space would be its cross section, so how strongly it interacts with the standard model. On the y-axis and on the x-axis is of course the mass of the dark matter. And so we can sort of parametrize our ignorance of this interaction by saying, okay, well, maybe the dark matter can interact with all of the particles in the standard model, but let's just consider two orthogonal channels, two independent channels. The channel where the dark matter interacts just with electrons, or leptons generally, and the one where the dark matter just interacts with nucleons, with protons and neutrons and things that contain quarks. Okay, so those are going to be the two independent channels that we're going to be looking at, and so that's on the y-axis. And generally, the sensitivity curve or the exclusion region of any given setup is shaped kind of like this. Okay, so at higher masses, you lose sensitivity. So everything above this this dark region is sort of either ruled out, or you would have sensitivity to it. And high dark matter masses, you sort of have diminishing returns in a 1/m trajectory, and that comes from the fact that you're just losing flux through your detector. That's the number density argument that I told you about before. And similarly, as you go to lower and lower masses, eventually you suddenly lose all of your sensitivity. Okay, and we talk about a minimum dark matter mass that your detector might be sensitive to, and that scale, that dark matter mass, is just set by the threshold energy of the transition that you're trying to drive. The transition between psi I and psi f costs you a little bit of energy. And so that sets a minimum dark matter mass that you can be sensitive to. And finally, what tells you how deep you can go in this cross-section space is the signal efficiency, right? So how likely it is that whatever transition you're generating is going to give you something visible, but also the background rate, the noise that you have to peer over. And so, yeah, the name of the game is to sort of minimize backgrounds and maximize signal efficiencies, but also to find state psi that minimize the threshold energy for some transition. That allows you to really delve deep and search as wide an area as possible. And so now I'll just give you this gigantic range of mass scales that is so large that it's really hard to conceptualize, but I'll just point out a couple of road signs along the way. So starting from the far left, we have dark matter that is sort of a 10 to the minus 22 eV. We call this fuzzy dark matter. I think Tracy did a pretty good job of talking a little bit about how to think about that as just some large wavelength wave that it can only be as large as the smallest scale that we observe in dwarf galaxies. And above that, you start finding dark matter candidates that we call axions or axion-like particles. These are bosonic things that behave a little bit like photons, but they're not exactly photons. As you go to even higher masses, you have dark matter candidates that are EV scale bosons. So these are things that have the energy of visible light, and they can be absorbed onto your detection material, and you can look for these things that way. And above a keV, something interesting happens. At above a keV, you're allowed to have dark matter that isn't just a boson, that doesn't just behave like a force carrier or something that can absorb, but something that you start being able to act like a matter particle, like something that can really strike and bounce off. And this happens around a keV, above which you have this sub-GeV dark matter parameter space that I'll come back to. But I think everybody's favorite dark matter candidate for the last 30 years was the canonical WIMP. So the canonical WIMP lives between about a GeV and 100 TeV. And these are weakly interacting massive particles. I'll tell you about why they're so well motivated, but this is where most of the effort in the community has been dedicated to looking at. At the far end of the scale, near the Planck mass, where that's the mass limit of what a fundamental particle can be, you have ultra heavy dark matter, matter that's about as heavy as a grain of sand, traveling hundreds of kilometers per second. So these sorts of dark matter particles leave macroscopic tracks in solid material. And so this is sort of a broad overview of how you go about detecting these different kinds of dark matter. And really, I want to draw contrast between the canonical WIMP space and the sub-GeV space, because while they are very similar by all accounts, the difference is that the canonical WIMPs leave rare but fairly energetic tracks, whereas sub-GeV dark matter particles have very feeble recoils that lead to just single quanta transitions. And so you need very different techniques to detect those. So now let me tell you about WIMPs and what we call the WIMP in very large quotes, the WIMP miracle. And all of this is to say that if you just ask, well, how do I make dark matter that has the right density today, that has this right 5-to-1 ratio with regular matter? You might imagine that the dark matter was in thermal equilibrium with the early universe, right? That it was hanging out with all of the other standard model particles when the universe was hot. And if you just say, okay, well, maybe the dark matter and the dark matter particle and dark matter antiparticle are annihilating every time they come into contact with one another, you can solve the relevant equations and find that as a function of time, they follow this initial black line. So this is the co-moving number density. This is just the concentration of dark matter in the universe. As they annihilate, that number density is decreasing as time progresses. But at some point, the universe is expanding so fast that the likelihood of two of these particles meeting and annihilating becomes very, very small, and the concentration freezes out. Okay? And so you end up with a situation where the final density, the final abundance of the dark matter is really just set by this this annihilation cross section, the strength of the interaction between two dark matter particles and how they annihilate. And there's this interesting coincidence where if you just close your eyes and say, well, this interaction strength, the thermally average annihilation cross section sigma v, if I just put a numerical value that is typical of weak scale interactions, and what I mean by weak is the kind of interactions that we see in the weak nuclear force, you get the right relic abundance. You get the right abundance of dark matter in present day. And so this was sort of very leading, because you can then cast this into many different theories that exist, things like supersymmetry, have candidates that follow a freeze-out pattern. And so everybody thought that's great. That predicts a dark matter particle that has masses that are of the order of all of the other heavy particles that we see in the standard model, things like protons up to Higgs bosons. And they should interact with roughly weak cross sections. That's great. We know how to create particles that are that size, and we think that we know how to detect these things. And so people went out and they built these great big detectors that are filled with liquid noble gases, predominantly xenon, and these are the real workhorses of the WIMP search. Okay, so what's happening here is that you have a tank with tons of xenon. Why xenon? Because the nuclei are heavy in xenon. And what's happening is the WIMP is going to come in, it's going to strike the nucleus of a xenon atom, and it's going to ionize it. And that initial ionization is going to generate two signals. The initial flash of light from ionization, we call that S1, and then the electrons that are liberated are going to drift in an electric field up to the top of the tank and are going to give you some current. We call that S2, okay? And these tanks are so incredibly successful at understanding their noise, at lowering the radioactive background, and really understanding what sorts of things can ionize xenon, that they're able to really start digging down in the dark matter nucleon cross section space. And so here on the left is a plot of what some of those exclusions look like, and you can sort of ignore most of the lines. Okay, I'll show you the trajectory in a little bit, but what I want you to notice is that there is a looming fog of neutrinos that is in blue along the bottom. And what's going to happen is as these machines get more and more sensitive, they're going to start seeing signals from neutrinos that come from the atmosphere and the sun. Okay, and when that happens, that noise is going to be so bright to them that they're not going to be able to tell the difference between a signal and a neutrino very easily. Right, the amount of time that they need to run their machine no longer scales linearly. You have to scale quadratically or to the third power, and so you get diminishing returns once you start seeing the so-called neutrino fog. So what's been the trajectory of these WIMP searches over the years? So from the 80s to today, there's been a sort of full steam ahead approach to this program, and these different detectors have gotten just exquisitely sensitive to particle recoils. So here in the x-axis, you have this cross section with nuclei, and the x-axis is time. And what I want you to see is that very soon, if you follow this trajectory, you're going to come up against this atmospheric background. And in fact, the xenon experiments have already begun to see the beginnings of this neutrino fog. There are papers that came out this year saying, look, we now have signals that look like the coherent neutrino scattering background, and that's fantastic. It's one of the few times that we've detected this coherent background. Sorry, the coherent signal. But it also tells us that, you know, we're coming up against the wall of how we can use these tools to search for WIMPs. Just for context, the kinds of scales that you might expect these cross sections to appear in are here on the right. So something interacting like through a Z boson, a weak mediator, is up there, where if the dark matter was interacting through some loop suppressed process, you might be down here where it says loop. Okay, so what is the actual status of things? So here is here's a plot from a GitHub repository that I absolutely love. This is from Shirian O'Hare's GitHub repository, where he accumulates constraints from the entire community, and he sort of keeps this as up to date as possible. And I really want to plug his work because he's doing an amazing job for the community of keeping everything organized. And I'll also point out two reviews on dark matter and direct detection here at the bottom. Okay, so what is this showing? What this is showing is that the liquid noble gas detectors, which are listed here on the top right, are really the workhorses. They're doing a lot of the work of probing through this huge parameter space and onto the neutrino fog. But there's other kinds of detectors that live here, right? So scintillators, which are crystals that shine when particles knock into them. like cosine and crust are also well represented. So crust is particularly sensitive to light or dark matter below the mass of a proton. You also have detectors that are based on bubble chamber technology, where a particle will come in, will interact with some supercritical fluid, it will generate bubbles, and you can directly look for these bubbles. So that's this pico 60 line. And finally, you have bolometers. And by bolometers, I just mean the world's most sensitive thermometers. These are crystals that are sensitive to very, very tiny energy deposits as they raise the effective temperature of these cryogenic crystals. And so crust is not just a scintillator, it's also a bolometer, and so is Edelweiss. And again, they have their best sensitivity towards the lighter end of things.
I have a question.
Yeah, go ahead.
Yeah, so earlier you talked about the WIMP miracle,
Yeah,
and you had some expected value for sigma times V. That
that's
was
right.
dark matter collisions, I presume.
Yeah,
And the cross sections here are dark matter nucleon.
yeah.
So it's a different beast. But is there some expectation of what the WIMP miracle value might predict for this object?
Yeah, sure. It's not a very tight prediction, right? So it's exactly these things on the right here, right? So depending on how you choose to arrange your diagrams, you might predict that if you just had a heavy boson being exchanged with couplings that give you sigma V, like I had in the previous slide, that you would be up here at 10 to the minus 38. Well, we've ruled that out, and so we have to adjust that to maybe they're exchanging something like a Higgs particle, something like a scalar, and we've ruled that out. And finally, so we have to say, well, okay, maybe they're exchanging something that allows sigma V to be large, but that is suppressed to interactions with nuclei, and that's why we say, okay, maybe they're interacting through a loop. They're interacting through a channel that has some mass suppression due to a virtual particle that's running in there. And so the answer is yes, we can make predictions based on the WIMP miracle arguments of cosmological production, but that doesn't give us an exact line on this plot, right? In fact, anywhere north of 1 GeV and like between 10 to the minus 38 and 10 to the minus 50, any model builder can come up with a reasonably well-motivated model that fits that. That's why it's important to try to go as far down on this parameter space as possible, is because there's a lot of well-motivated models that live pretty much everywhere here. Does that kind of answer your question?
Yes, yes, thank you very much, yes.
Okay.
But I guess I don't see therefore the end game. You can keep pushing this down as much as you want, but
Right.
you still be in some sense consistent with the 10 to the minus 26.
Yeah, that's right. That's right. And so the end game here is in some ways a practical one. And the secondary end game is, a theoretical one. A practical one because you really can't peer beyond the neutrino fog too far, right? So the end game seems right now to be, this is low-hanging fruit. It's well-motivated fruit. We go down to the neutrino fog, and we close the chapter on the spin-independent WIMP interaction picture, okay? Theoretically, the kinds of WIMPs that we've been able to come up with that are sort of the gold stars come from supersymmetry, and those really sat here in the range of like 10 to the minus 44 to 10 to the minus 48, right? And so right now we're really looking at prime real estate for what sort of these grand theories were predicting. And so once we get to the neutrino fog and below, it does seem a little bit harder to motivate things that interact that weakly.
Yeah, thank you.
Yeah. Okay, so looking forward, what does this look like? Okay, so above a GeV, the name of the game is, well, we've made these multi-ton xenon detectors, and we've designed these things that are incredibly sensitive. They've been incredibly successful in probing this parameter space, let's just keep doing that. We're going to build a next generation Xenon machine, and we're going to go all the way down to the neutrino fog. So that's this gray line XLZD. In the light dark matter side of things, it becomes more complicated, right? So here, things become a lot more difficult because dark matter is a lot less efficient at delivering recoils to atoms once it's lighter than a proton. Okay, it's just not very well kinematically matched, and so you have all sorts of different proposals for how to go about it, right? But they all sort of follow the same theme of saying, well, you know, you have a fluid, you generate some ionization, and you try to track the flow of this ionization towards the edges of your chamber. You might have a scintillator or a bubble chamber, what have you. We think we understand how to move forward in this parameter space.
I have a question.
Yeah.
In the neutrino fog zone, is it possible to use the type of particle, bosonic versus fermionic, for example, to make, I mean, can you rule anything out about particle type? Or using, is there anything that's sensitive to spin or to polarization that could help us?
Yes. There are techniques. There exist techniques that can peer through the neutrino fog. I think one of the most obvious is directional detection. Okay, and I'll talk a little bit about that later on. But the neutrino fog is a background that really comes from the atmosphere and the sun, and so roughly speaking, it has some directional aspect to it. Similarly, the dark matter isn't exactly isotropic; it's coming from a particular direction to some extent. And so, if your detector can tell the difference in direction of the recoil, you can do quite well at beating the neutrino fog. That is one way. Talking to spin is another way, right? If you're looking for dark matter particles that talk to spin differently than neutrinos, then you can go after it that way. You're right. But this is sort of the most naive thing that you can do, which is just hard scattering with your atom, right? Broadly speaking, this is sort of the most naive thing that you can do, and really represents the state of the field as a whole, not one model in particular.
Thank you.
Carlos, a quick question.
Sure.
Does this, looking at this exclusion plot, are we really ruling out WIMPs, would you say? We've really tightened the bounds, right? So I understand we're kind of hurtling towards ALPs, but this is looking pretty bad for WIMPs, isn't it?
Well, it is and it isn't. Depending on who you ask, this is either really bad or really good. Okay, I think the defeatist attitude that we're about to see the neutrino fog and therefore we've ruled out WIMPs and dark matter is in crisis is not very, you know, it's not a very well motivated point of view, because there are several different channels that take the WIMP and open up new parameter space, right? So you'll notice here on the y-axis, this is a spin-independent interaction. As soon as I turn on spin-dependent interactions, the parameter space clears up significantly. We're much less well adapted to look for spin-dependent interactions than spin-independent interactions, and there are orders of magnitude of open parameter space in this mass range for that kind of WIMP. And also, the WIMP picture that I told you about, this freeze-out picture, really just depends on annihilation being the one thing that holds you in equilibrium in the early universe. And I'll tell you how a small modification can really change the tone of the conversation. So hold on to the second part of that, okay?
Yeah, thanks.
Cool, okay. So now we move on to non-wimpy dark matter. And yes, the Alps and the axions that live south of 1 eV, we'll get to that if we get to that. But really, the thing that I want to impress upon you is that the canonical WIMP picture that has annihilation as its main channel for establishing equilibrium and therefore setting its relic abundance by freeze out is The lowest lying fruit on the tree, right? There are very small modifications that you can do that change this significantly. For example, if it wasn't annihilation that set equilibrium, but instead it was elastic scattering, or it was an interaction that changed the number of particles, right? Like 3 to 2 processes set the equilibrium. You still have this this picture where you ride the equilibrium line to some freeze out point, and then you sort of move away from equilibrium and you set the Rayleigh abundance, but now you have a different channel that does it. And so the cross sections and masses that you predict are going to be different. That is a very small change that you can make to your model, and all of a sudden you allow the dark matter particle to live in much lighter dark matter masses, and you allow it to sort of take on a different character. Another way to sort of move beyond the WIMP is to look at situations where the dark matter was never in thermal equilibrium with the early universe. A so-called freeze-in scenario. And so what a freeze-in scenario is a situation where the early universe had essentially no dark matter. The dark sector was completely empty. And it was out of thermal equilibrium, of course. It wasn't in thermal contact, but it still has a very small interaction channel with the standard model. And through this very small interaction channel, what happens is the standard model starts to generate just a little bit of dark matter, okay? And so as time moves on, you generate more and more dark matter until eventually the standard model can't talk to itself hard enough to generate the dark matter, and you sort of plateau out, okay? You freeze in. And here the predictions are exactly inverse to a freeze out picture where an increasing coupling actually increases your Rayleigh abundance, okay? This is, I think you'll agree, as minimal a picture as the freeze out model. You just don't get this interesting coincidence that weak scale masses and couplings give you the right Rayleigh abundance. But numerology aside, as far as models go, this is just as well motivated as the freeze up picture. And not only that, this gives you a very tight line of the predicted interaction strength and cross section, and I'll show you that in a second. Okay, so let's move beyond WIMPs, and if we want to move beyond WIMPs, I got to tell you a little bit about what the interaction rates look like in these detectors. There's only a few bits of math in the presentation, and you can, for the most part, ignore the details of the math, okay? What I want you to take home from this is that the rate, capital gamma, really just depends on three parts that can be factorized from one another, generally speaking. The blue here, eta, is the mean inverse velocity. So that's just the astrophysics of the problem. That tells you about how the dark matter is distributed in velocity space. The red, which is the particle physics of the problem, is a way of parametrizing our ignorance of how the dark matter scatters with regular matter, okay? And if that is just some constant value, then that would tell you that the dark matter interacts through some contact interaction. But if that has some Q dependence, some momentum dependence, that might tell you that it's something like a long range interactions, that it's talking through a very light mediator, okay? And that kind of brackets the probabilities, the possibilities of spin independent interactions. And so we'll use these two limits as the two limiting cases in the bracket. And finally, this thing in orange is the transition form factor. And that really is where the condensed matter or the chemistry come into the problem, and where we're discovering that this really requires a new approach to this. This sort of requires us to talk to people that are in different departments. And what this object tells you, it's what's the probability of absorbing momentum as you go from some initial quantum state to some final quantum state, okay? It turns out condensed matter physicists, chemists, material scientists have dedicated a lot of time and effort to deriving this object. There's a million different names for this object. Different people call it different things. We call it a transition form factor. But in some sense, this is where the art lies, is in trying to devise materials or setups that optimize this orange to scenarios of blue or scenarios of red that might be of interest. Okay.
Carlos, you were described just earlier how depending on what kind of physics is setting the freeze out uh, number density of dark matter, that could change depending on what was happening before the freeze out. So how does that reflect in FDM here on this picture, or does it at all? Like the cross section, yeah.
It doesn't really actually, right? So this is why it's difficult to take a prediction in the annihilation cross section and cast it into a prediction of the scattering cross section. In general, the kind of things that give you annihilation can come from either in exchanging heavy particles or light particles, and that might not make a huge difference in the early universe for annihilation, but as you'll see, it makes a pretty big difference for scattering. Right? And one way to see this, one example of how it can change things, is that in the early universe, dark matter can be relativistic, or it can at least be moving quite fast. Okay, it can be quite hot. And so if you have a momentum dependence to your interaction, it might be behaving one way in the early universe, but now when it's relatively cold, it might be behaving in a totally different way.
I see. Thank you. Thank you.
Sure. Okay, so let me now give you the same order of magnitude estimates for the sub-GeV dark matter parameter space. And so from here on out, capital R are nuclei, little r are electrons, and it turns out now separating these two things is going to be rather important because the dark matter is very efficient at exchanging energy and momentum with electrons when it's light, not so much with nuclei. Okay. As far as the imparted momentum goes, for dark matter that's an MeV, so 1,000 times lighter than a proton, the momentum that's available to you to exchange with something like an electron is of order keV. Okay, but the energy budget now shrinks. It now becomes of order eV. And in the case where you're just absorbing the dark matter, if you have a bosonic dark matter and you're just absorbing it onto an electronic state, then the energy equals the momentum. It's just a vertical transition, okay? And so right off the bat, a person or a material scientist looking at these orders of magnitude would immediately say, this is a totally different beast. Our energy budget is no longer in the X-rays. Our energy budget is now something that is invisible. Right? It's from the IR to the UV. This is where benchtops chemistry sits. This is where condensed matter sits. That's why the cross-disciplinary aspect of this is important. So I'll tell you about the workhorse detector in this range, okay? The idea is, well, how do you go about detecting particles that are visible, that are, that have energies that are visible? You just use a camera, right? Everybody has a camera in their pocket. These cameras work using devices that are called CCDs, charge-coupled devices. And generally speaking, what happens is that it's a chunk of silicon, it's a chunk of semiconductor. And when something comes along and excites its electrons, those excited electrons get trapped. Okay, they're trapped in a pixel, and that excited charge can just sit there for some amount of time until it's read out by the electronics. Okay. It turns out that this is a pretty good way of looking for sub-GeV dark matter if you're quite clever about how you're reading out these charges, right? So in your phone, the error of how much charge is stored in each pixel is quite large, but it doesn't matter because each pixel has a lot of charge generated, okay? There's a lot of photons hitting it, so we just don't care about that. When we're looking for dark matter, on the other hand, we really want to lower the noise as much as possible, and so we use, for example, what are called skipper CCDs, right? So this is sort of the flagship experiment right now, Sensei. And what they've been able to do is they've been able to take pictures of the dark, okay? And what they've been able to show is that they have a way of reading out these charges so sensitively that their uncertainty in how much charge is stored per pixel falls below 1 electron, okay? So they take a picture in the dark and they have a bunch of pixels in a row and they say most of these have exactly 0 charge, no interaction. Some of these have 1 charge, 2 charges, 3 charges, blah, blah, blah. And you can look for direct electronic recoils this way. And they have been remarkably successful at using very sensitive cameras to take pictures of dark rooms. So what does that look like in parameter space? So here I'm showing you the dark matter electron cross-section for something like a heavy mediator, okay? So something where the FDM is equal to 1, or a contact interaction. And these silicon CCDs, so Sensei and Domic M, are up here, and they're really pulling most of the weight below about 10 MeV. Above that, you still have the noble liquid noble detectors doing really quite well. And they're just looking for ionization of atoms, right? And so the reason why these are two separate paradigms is because the liquid noble people are looking for ionization, situations where you take an electron and you liberate it and becomes a quasi-free particle that does things, okay? Whereas Sensei and Domic and things that fall below about 10 MeV are looking for bound-to-bound transitions, where you go from ground state to some bound excited state, and you have to trap it and you have to be able to detect it, okay? And these single particle transitions are very difficult to find in general, and that's why these things work very differently. The kinds of theory targets are much more well defined in this space, right? So here we have situations where we might look for a freeze out situation of what we call elders or SIMPs. So these are elastically decoupling dark matter, where the channel that sets the relic abundance might be elastic scattering, or these 3-to-2 processes. And we can also take a look at the light mediator case, where now you have a momentum dependence to your interaction. And the theory target here becomes freezing. And so this is that tight line that I was telling you about. It makes a very concrete prediction for a model that seems to be, one of the few models that you can put in this space, but it's a real good model that consists of an ultralight dark photon that freezes in some dark matter particle of order an MeV.
So that depends on the mixing angle, on the kinetic mixing angle with the regular photons?
Yeah. Yeah,
And-
yes. So you can cast this in that parameter space. Yes.
And if you did, what are you assuming? When you get that narrow band there, you're assuming some constraint on the kinetic mixing angle?
Let me think about that. So the thing that you're assuming is that the mixing angle is the thing that sets the relic abundance. That's your one free parameter in the theory, right? And so in order to freeze out to the correct relic abundance, you just set the mixing angle to give you that freeze in abundance. Does that make sense?
You set the mixing angle to give what?
The correct relic abundance, right? So the mixing angle determines how feebly you interact with the standard model, and that is what allows you to populate your dark sector.
I see, okay.
Right.
Yeah.
So that's why it becomes so thin. Okay. Good. So this is generally the state of the art, where you have these skipper CCDs, these semiconducting based detectors, are really quite tantalizingly close to peering into the theory target space, and that's great. But let me give you that in context, the context of the field over time. So back in 2017, we put together this community report, the US Cosmic Visions report, where we were trying to say this is the general trajectory of dark matter research. And we put together plots like this, where we said, okay, this is how we envision the search for sub-GeV dark matter. And there still are a huge amount of proposals of different materials and different strategies to look for these kinds of interactions. But the thing to read from this plot is that, generally speaking, these can be broken up into short-term, medium-term, and long-term proposals based on whether or not this was mature technology where we could understand it in short order, and things that seemed like good ideas at the time, okay? But importantly, we said, well, in 2 to 5 years, we'll be in the medium term regime. We're going to be down at 10 to the minus 40 square centimeters, and it's going to be incredibly successful. Well, it's been more than that now, and we're still up here at 10 to the minus 36. Okay, so what happened? Well, it turns out being down at 10 to the minus 40 involved making some assumptions about how much we could reduce backgrounds. And that's really a problem, because the theory goals live exactly in that intervening space. Okay. So, the question is, well, how do we learn from that the community as a whole, may be seen as having come up short. And that's just that we have to deal with backgrounds, right? That's the real obstacle. There are 6 orders of magnitude of potential reach waiting if we can just deal with the backgrounds inherent in these low threshold detectors. Okay. These very optimistic lines assume 0 background for things like 1 kilogram year of exposure. And you notice that a lot of those dotted lines reach down to roughly the same area. And that should not be a surprise. Okay. Catherine Zurich, who's one of the big experts in the field, once said that everything has a dynamical structure factor, which is code for if you hit any material hard in the electrons, it'll get excited and it will produce something that looks like a signal. Okay. And so we can compare, for example, a 1 kilogram of silicon and its 1 electron excitation rate, so quote unquote 0 background, to 1 kilogram of organic molecular scintillator, EJ301, and we find that, to within a factor of 2, they're pretty similar. Okay. The techniques that you use to read out those signals are what sets the difference. It's what allows you to be able to beat back these backgrounds and delve into these 6 orders of magnitude of potential reach. And one of the ways that you can do that, one of the ways that you can beat the backgrounds, and one of the ways that that you can beat backgrounds like the neutrino fog, is by generating some directionality in your material, right? So why is that important? Well, here again, we have our dark matter halo, and I've cheated you at the beginning because we're not at the center of anything, right? We're off to the side, and so we don't see this perfectly isotropic thing. We actually see an effective dark matter wind. And because the Earth is tilted on axis with respect to the wind, that means that if at noon the wind is coming from your ceiling, 12 hours later, it might be coming from one of your walls in your lab. Okay, so if you have a detector that can tell the difference between a particle recoil coming from the ceiling and coming from the wall, that might be a good way to get a handle on whether or not what you're seeing is dark matter or just the isotropic stochastic background that might be in your laboratory. As an example, I'll tell you about one of my favorite ways to look for directional detectors, which is to go across the quad to the chemistry department, where they have things like this. This is called transstilbene. It's a molecular crystal that scintillates. Really, it's a planar molecule, and these planar molecules like to crystallize in ways where their faces are roughly pointed in one direction. We've known about transstilbene for a long time, and so we can create rather big optical quality crystals. And what's interesting is that the electrons in these molecules, you can think of them as being free to roam around the perimeter of the molecule. And so because these states are not spherical, they have some aspect ratio, you can convince yourself heuristically that the likelihood of exciting them is different in different directions. And it turns out it is. We can go out and we can compute what those probabilities are as a function of direction. And then the idea becomes, well, you have a detector volume, you fill it with these chromophores, I'm going to call them that now, that are just particles that emit photons when they're excited. Notice I'm not calling them scintillators anymore for subtle reasons, but the idea is still the same. You have molecules in a vat, dark matter comes in, excites them, and it gives off photons, okay? Nature is quite kind to us here because generally speaking, molecules are transparent to their own emission. And so that means that if you excite a molecule and it gives off a photon, 65% of the time, thereabouts, you'll detect that photon on the surface of some large crystal. And so you can compute what the fluorescence rate, what the rate of photon emission might be throughout a day, the so-called daily modulation. And you find that for these kinds of molecular crystals, or for really anything that has this fundamental anisotropy, that rate varies over the day, right? So these are experiments where you still have your vat of cold fluid in your lab and you're detecting photons or what have you. And instead of looking for hits, once every, month, you're looking for a glow, a very dim glow that changes throughout the day. And that variance throughout the day is quite a verifiable signal. It doesn't look like the stochastic background that we expect to be contaminating our labs from thermal neutrons or what have you. And so that allows you to gain about 2 orders of magnitude in sensitivity, right? So here are projection curves for these still beam scintillators, right? And up here, oh Jesus. Up here in the dotted lines are what the sensitivities would be, assuming a realistic background rate, but saying, okay, we have no directionality. How good can we do? Well, unsurprisingly, about as good as the silicon detectors are, right? But now we introduce this directionality, and we look for a daily modulation, and all of a sudden we gain 2 orders of magnitude in sensitivity. We go down to this black line in exclusion potential. But because we have now a verifiable signal, we also get a discovery potential. We get something that we can compare to a model and say, yes, that's what we expected. That's what we got. And it turns out that being able to talk to chemists in the community and condensed matter physicists, you find out that this is not new technology. In fact, a kilogram of strand still beam can probably be found within a few blocks of where you're sitting right now. It's incredibly inexpensive. You don't need to employ, a fifth of the national budget for dark matter to create these sorts of things. You can just go out and make it and get quite a good return on investment to go down and peer into these theory lines by several orders of magnitude. Okay, so maybe in 2 minutes I'll tell you how to go after the nuclear recoil, right? So we talked about light, dark matter being able to efficiently scatter with electrons, and how to go after that. Now let's talk about the next step in complexity, which is when you knock into the nuclei, okay? So there, it turns out one of the few ways to go after this channel is through the Migdal effect, okay? So what is the Migdal effect? It's a situation where the dark matter comes in, it knocks into your nuclei, and it sets it streaming. It causes a fast recoil. And so from the point of view of the electrons that don't have enough time to react, they now see a charged particle that's moving quite fast in their vicinity. And so the probability that they will get ionized, that they will get excited, is non-zero, and that's what you look for, right? This is an inelastic excitation channel, and so it allows you to go to lighter masses. You suffer a slight kinematic penalty because of this, but it gives you a lot. And in fact, in a previous plot, you can see what this Migdal analysis does, right? So this is that dotted line up here that takes xenon, the xenon sensitivity that usually goes to essentially 0 at a few GeV. It allows you to extend it down by an order of magnitude to hundreds of MeV. So this is a pretty successful way of searching for lighter masses using existing detectors. And so a natural thing that we asked was, well, maybe this exists in the kinds of detectors that you can use to already look for sub-GeV dark matter, like the molecules that I just told you about. And so if you sit down and you analyze the problem, you find out that these Migdal like analyses can be done, and that in molecules, in fact, there are two different kinds of Migdal effects. One that comes from shifting the total center of mass of the molecule, and one that comes from internally deforming it, crumbling it. And that you need to be careful about how you treat these two different Migdal effects, but they exist. And so it allows you to then use that kind of detector that already exists to look for nuclear scattering. Not only that, but because these detectors are anisotropic, you still get this daily modulation. And so that's great. It allows you to beat down background in that way. And so some take-home messages about the Migdal effect for light-dark matter scattering, especially in these kinds of detectors, are as follows. One, the center of mass recoil effect is subdominant at all masses. So this is for some, this is an analysis that was done for some toy molecules, carbon monoxide and nitrogen. And this other effect that comes from crumpling the structure, it has a very favorable kinematic factor that dominates the sensitivity at all masses. Here in the red is the equivalent, quote unquote, Migdal rate in silicon, in a semiconductor. And so one of the big questions in the community until last week was, what kind of Migdal effect is this that we've been calculating for silicon? It turns out it is a non-adiabatic effect. It turns out you can show that this comes from purely effects beyond the Born-Oppenheimer approximation, and that's great because it allows us to think about this slightly different than the way that we think about the Migdal effect in atoms like xenon. Okay, so this is maybe a good place to end because it sort of tells you about the orthogonal part of the orthogonal channel. So I'll probably just take questions here.
I had a question
Sure.
quickly. So these experiments, I mean, you're worried about background and noise and stuff like that. So are they all ultra cold experiments? I mean, do you cool the detectors or is it not necessary?
Yes, absolutely. So all of these detectors are run at cryogenic temperatures. For the most part, they're extremely cold. So the thing that sets how cold they need to be is the energy of the transition that you're interested in. So if you're looking at transitions of order an EV or 0.1 EV, then you have to be colder than thermal excitations, and so you really got to cool these down. So yeah, you should think of all of these experiments as being essentially some variation of a camera looking at a chunk of material, and that chunk of material is in a totally light, tight, very, very cold box, probably buried under a mountain.
Thanks.
Yeah.
I had a question as well. So I was curious about your introducing anisotropy through rotation of the Earth. So
Okay.
you noted at some point that the linear velocity essentially of dark matter would be around 300 kilometers per second, but
Mhm.
the rotation of the Earth on the surface of the Earth would contribute a very small linear velocity, right? Maybe
Yes.
like half a kilometer per second or something. So, or much smaller, or something like that. Is that enough to actually generate this anisotropy and thus drop your sensitivity by such a large amount, or am I missing something?
No. Okay, good. So this is a really good question because this is a confusion that comes up a lot. The anisotropy that I'm talking about isn't coming from a change in the absolute value of the velocity over time. It's coming from a change in the direction of the dark matter speed over time. Right. So the dark matter is still traveling at roughly 300 kilometers per second. It's just coming from a direction that changes throughout the day. Right. And so like I told you in this slide, this molecule will only get excited if the dark matter hits it on the long axis. Okay. So if you align all of these structures such that at noon they're aligned with the dark matter wind, but 12 hours later they're facing it face on where they're much less likely to be excited, then you get this daily modulation. That's why what we're talking about is the directionality of things, not the change in the linear velocity. Does that make sense?
Yeah, yeah, absolutely. I was just a little confused. Why could you not do it at the same time with two crystals oriented in two different directions?
Yeah, you got it right on the nose. So, let me show you what we're actually working on right now. So this is a marriage of the two technologies. This is an ongoing collaboration called Diana that is doing exactly that. Is going to take several crystals. So these are, it's something like an ice cube tray, and in each basin you have a different crystal with a different orientation. And the light is now being read out by a skipper CCD. So it's basically using something like Sensei to read out something directional like the crystal that I just told you about. So that is exactly the idea, is you have several different crystals in different orientations, and you're looking for these waveforms to trace out some path in signal space.
I see, thanks.
Sure.
So what's your own intuition about what dark matter is after all this?
Yeah,
Assisting us.
that's a very good question. So I kind of wish that I had added this slide to my talk. So normally what I do in like informal situations is I have a QR code that you can scan and take a vote on what you think the dark matter is. And I can share with you roughly what the results are. So let me go down to where I have.
This is the result of a survey.
Yeah, so these are the result of the survey. The survey goes like this.
Back to us.
Sorry?
I said you turned the question back to us, to the audience, right?
Yeah, a little bit.
Okay.
Because look, I'll tell you what the crowd thinks, and then I'll tell you what I think. Okay? Good. So the query usually goes like, okay, I have roughly speaking these four types of candidates. Okay, canonical WIMPs, axions, which I didn't tell you about, light dark matter, and ultra heavy light dark matter, and people vote, and overwhelmingly the camp goes towards canonical WIMPs, right? With roughly like a third of people voting canonical WIMPs, roughly a third of people voting axions. And then the rest of it is split between light dark matter, I don't care, or things that are not in this parameter space. Okay. And it's surprising how that distribution has changed over time. I think 15 years ago, if you were to ask, theorists, most people would say, no, it's canonical WIMPs, right? It's supersymmetry. The LHC hasn't turned on, it's got to be supersymmetry. And now, like these machines have turned on that make it less and less likely, although the WIMP is not dead. A lot of the interest has shifted towards lighter and lighter dark matter. Right. And so axions sort of become the new belle of the ball, because they're a very natural dark matter candidate. They solve this other underlying problem in particle physics called the strong CP problem. Invite me back again, I'll tell you about it. But that seems to be garnering a lot of attention, and a lot of it has to do with the fact that, well, maybe it's not enough to just have a model that predicts dark matter. Maybe you need to have a model that, does that and solves some other problem and makes you a drink, like this is the way that people operate. Personally, I think that dark matter is probably still hanging out in between about an MeV and 10 GeV. Okay, to me, most of the models that I can write down, and this is my bias, is coming from a model building background. Most of the models that I can write down live in that parameter space, right? And the easiest changes to the lowest hanging fruit give me something that lives in that space. Yeah, I would be surprised if the universe doesn't have axions, but there is absolutely nothing that tells me that if axions exist, they must be dark matter. So that's my point of view.
Okay, thank you.
Thanks so much, Carlos.
Yeah.
Let's see one more.
Thanks for having me. Thanks for listening.
And we look forward to hearing again at the time.
Yeah, I'll see you next week.
Yeah.
Bye.